Hi everyone. My name is Nayana. I'm currently the president of the club as well as the project lead for the Indie project. My main motivation behind this workshop was to provide everybody with a general overview of the field of robotics. Because I feel like, especially when I started looking into this field and becoming interested in it, it was very intimidating to figure out where to start or what exactly was in the field. Obviously, the field is very expansive and I can't cover everything in the short amount of period of time, but hopefully this workshop will give you a nice overview where you can gain a general sense of the field. And so just to cover a few examples of like robots we've seen, because they become more and more commonplace in our like day-to-day lives. Some examples are mobile robots, which are ground vehicles, as well as like Roombas that we see for like cleaning robots. Another instance is aerial robots, such as drones. Another is walking robots, such as Atlas and Spot that we see from Boston Dynamics, as well as underwater robots that are used for surveying underwater environments, and then industrial robots, which are used for construction and manufacturing applications, and they're primarily stationary. So looking at the big picture, robotics as a whole is a very interdisciplinary field. It's unique in the fact that normally in our coursework, we only focus on one of these areas, whether it be mechanical, electrical, or software engineering. But the unique aspect of robotics is that we have to learn about all three of these areas and learn how they all work together in order to form a like product. And so some overarching concepts that I'm going to cover are perception, which roughly translates to how I see and interpret the environment. Localization, which roughly answers the question, where am I in the world? Motion planning, which answers the question, what is my next goal? As well as controls, which is how do I get to my next goal? Yeah, and so roughly covering mechanical components. Obviously, this is more expensive than this one slide, but I feel like the most accessible component is motors. And so a broad overview is that motors convert other forms of energy into mechanical engineering energy. And so there's many different types of electrical motors. The first type is DC motors or direct current motors, which you can see here. These are great for continuous rotation and high-speed applications. And there's two different types, which are brushless versus brushed motors. Stepper motors, which you see here, these are great for low speed and high position control applications. And servo motors, which you can find here, which are great for high speed and high torque applications, but they have a limited angle of rotation. If this sounds interesting to you and you want to learn more about motors, we actually did a workshop a couple weeks ago that you can find at the link here. And you can go back and watch that presentation and learn more about all of these in more detail. Electrical components. Even though sensors aren't explicitly electrical components, I still feel they're important because using electrical engineering, we connect these components to our system. And so a broad overview of sensors is that sensors give us information about the surrounding environment. Some instances of this are LiDAR, which is lane detection and ranging. Essentially how it works is it emits a laser light and measures the reflection in order to give us a accurate range measurement. Radar is pretty wide, but it emits radio waves to act similarly and measure distance and range. GNSS and GPS serve as global positioning units, and they essentially use satellites to provide us global positioning information. So essentially provide us absolute information on where we are in the world. IMUs are used to measure acceleration and rotation, and then cameras, pretty self-explanatory, return pictures and videos of our surrounding environment that we can then use to figure out what we see. Covering software, the first area is perception, which translates to how we are able to perceive and interpret the environment. And as you can imagine, we have to interpret data from a large variety of sensors. I touched upon some of them before, but camera, LiDAR, radar, and more. And so we use computer vision algorithms to help interpret this data. One of the most common applications is object detection, recognition, and classification. And so this can entail detecting lanes, cars, stoplights, pedestrians, and other things. If you want to learn more about this, a great class to take is 1674, which is Intro to Computer Vision. And it's a really good class to gain a great overview of the common algorithms in the field. And so a pretty applicable example for self-driving cars is lane and vehicle detection. So as you can see in this example, we're detecting the lane and the green denotes a lane that we can travel in. So essentially we're using the left line for detection to check what the curvature of the path is or the lane is. And you can see that in the upper left-hand corner over here, where it's changing based on the line. And then the other portion is that we're detecting the car next to us, probably to determine whether or not it's crossing paths into our lane so we can form an alternate path on our road. So yeah, I took this from a autonomous vehicle driving repository where this guy implemented a large variety of computer vision algorithms specifically for the application of autonomous driving. If this sounds interesting to you, feel free to look at the source and look at the different repositories that this guy has. It's really interesting and expansive. So yeah. Next topic is localization, which roughly translates to how the robot infers where it is in the world. So essentially the main goal with localization is to utilize sensor data to form a belief of where you are in the world. So I guess I can illustrate this through an example. Imagine that you're in your current room and then you place a blindfold over your head and you remove all the furniture in the room. I then ask you, can you travel from one corner of the room to another? Odds are when you're traveling in your room, you're probably not gonna reach the other corner exactly. There's gonna be some amount of error that you have in terms of where you eventually end up. And so I then have the next situation, which is you're still have a blindfold over your head and ask you to travel from one corner of the room to the other, but now there's furniture in the room. So essentially, as you're traveling through the room, you can now touch things around you, such as your desk or your bed or your dresser, and you then adjust internally in your head where you are based on what you're like feeling. And so essentially, that's the main goal behind Kalman filters, which are a big overarching topic with localization. Essentially, the goal behind these are to estimate the robot's state, which are pretty much anything you want to like measure, but it roughly translates to position, velocity, acceleration, etc. over time given a set of measurements. And so on the most basic level, a Kalman filter acts similar to a low-pass filter, which basically means that it filters out noise. There are two different phases to a Kalman filter, which are the prediction phase and the measurement phase. Tying back to our previous example, as you're walking through the world, you're implicitly doing this because as you walk like an empty space, you essentially have a prediction like in your head of where you are. But once you touch your dresser, once you touch your bed, once you touch your desk, you then adjust your internal belief of where you are using a measurement to then say, okay, I am approximately in this area. So this is the basic idea behind a Kalman filter and how it helps us with determining where we are in the world. And so it goes without saying that the more senses you have, the more precise your belief will be. And so if you want to learn more about Kalman filters, a great resource is this PDF that I linked down below over here. And this document was written by a professor at UNC, and it provides a great step-by-step introduction to writing and implementing your own Kalman filter, as well as understanding the different equations and math that go into making one. And so I also used it for the example that I'm showing here. In this example, we're measuring voltage based on a ground truth. So the green line represents our truth value, while the black crosses represent our noisy measurements. So essentially, if anybody's worked with any sort of sensor, you know that with the sensor, there's a certain amount of noise that's injected into the ground truth value where you won't get the exact same measurement every time you measure. And so essentially we can see in this example that you can see in this example that in the beginning, as we go from the beginning all the way to the end, the amount of error decreases as we get more and more measurements, or as they denote here, iterations. And so this is further illustrated by this graph where you see there's a large amount of error in the beginning where we have few measurements, but as we continue, the amount of measurements decreases. And so this is a simple example with one measurement, which is voltage, but a lot of more interesting examples involve taking information from different sources such as IMU, GPS, LiDAR, radar, et cetera, in order to provide us like an accurate estimate of where we are in the world. Motion planning roughly translates to how do we have our robot reach its goal in a fast and efficient manner? And so the way we accomplish this is through different path planning algorithms, which help us plan our movement and avoid collisions. And so obviously there's many different representations we can use for planning, but the most simplest one is a grid. And the main goal behind it is that we want to navigate in free space. So what do I mean by free space? The most common form of that we use is an occupancy grid, which you can see here. The black squares essentially denote obstacles, which is places that we can't travel to, while white is the free space. And so essentially when we're planning, we want to figure out where we can travel in the free space to reach our goal. And so two different common performance metrics to achieve this are path length and time to solution. So essentially our main objective is how do we find the shortest path to our goal in the fastest amount of time? And some common algorithms to look into if you're interested in are A star, D star, and rapidly exploring random trees, which is ROT. And if you're interested and this sounds interesting to you, a great class that you can cross-register for at CMU is 16350, which is planning techniques for robotics. Probably one of the most common path planning algorithms out there is A star. And so you can see in this example that the rainbow boxes indicate grid cells that we've explored, while the green path represents our path. And we can see that as we explore more and more grid cells, we eventually find our best path to our goal. And so, yeah. Controls. A broad overview is that with controls, they're signals that we send to the robot in order to perform an action. We use different mathematical models, our vehicle state, and our goal points to determine optimal outputs for our desired action. The simplest model is an inverted pendulum, and some examples of controllers are PID, LQR, ILQR, and MPC. And if you want to learn more, a great class to take in the ECE department is ECE 1570, which is robot controls. So probably a simple example, tying back to my inverted pendulum example from before, is that with this example, the main objective is to write a controller that's able to balance this inverted pendulum upright. And so we can see in this example that the main objective is to, when we place different weights at the top, the controller has to balance the pendulum upright. And we can see that as we increase the number of weights, the pendulum eventually stands upright, which is pretty cool. So putting all this together, essentially when we start off, we take sensor data, which we covered before, all these different sources, and this feeds into our perception and our localization stacks. And so essentially with our perception stack, we essentially interpret the information from these sensors, more specifically our camera, and we say, okay, what do we see in the world around us? So essentially, it provides us information locally or close to us on what's going on. So for instance, in my example from before, with our vehicle and lane detection, an example of perception is that we would essentially be seeing, okay, where is this car relative to us so that we can avoid it. But again, going back to our diagram, we interpret images from our camera in order to determine what's going on in the world around us. And then all these other sensors, so radar, LiDAR, GPS, and others, feed into our localization stack, which essentially tells us where we are in the world. And then these two components feed into our motion planning stack. And the main motivation behind it is first out figuring out where we are, as well as what's around us. Because first, in order to, if you think about it, how can we move to our next point, or how can we move around if we don't actually know where we are? So that's the first thing. We have to figure out where we are. And then with perception, we figure out, okay, how's the area around us? Is there an obstacle in front of us? Is it free space? Can we move? Are we allowed to move? And we'll avoid a collision. So that's what our perception stack tells us, essentially gives us a map, similar to like an occupancy grid like this, but probably a little less cluttered. But it'll give us a map essentially of or local information about what's around us so that we can essentially plan around it. And then with our planning stack, we take in all this information and we essentially say, okay, how do we go to our goal? And we spat out a bunch of points, which we then feed into our controller, which takes in these points and controls us such that we can reach our goals. And so some further resources you can use if you're interested in robotics, besides being in our club, are Arduinos. Arduinos are a great first step to start tinkering with robotic systems and all these different concepts that we covered up on. Um, RAS, which is Robot Operating System. This is the general framework that's used on many robotics projects and applications. We're actually using it for the Indie project, but if you're interested, we actually did a workshop a couple weeks ago on RAS. You can take a look at that if you're interested in learning more. And another helpful resource that I found was Robot Academy, which is an open source robot like learning and resource. And essentially what it is a bunch of short videos that you can use to learn different concepts.